So, okay. All this work is in the framework of the Gaia collaboration, stands for Jets and Disks at INAF. And here you can see the list of my closest collaborator and the collaboration I'm going to talk about it. So a brief introduction of the star formation stages. You know that stars from the fragmentation of molecular clouds into prestellar cores. Those prestellar cores can eventually collapse because of their mass. When this happens, a protostellar object is formed, composed by a forming star, circumstellar disk, and a very deep envelope. By passing the time, the envelope dissipates, and we can see through the envelope the forming object, photosphere, and the disk. The material of this object accretes and accretes, so the temperature inside it also accretes until it reaches 10⁷ Kelvin and enters the main sequence, eventually also with the formation of a planetary system. So the question that will drive this talk would be how the stellar mass is built. So how it happens that from basically a cloud made by dust and gas, we ended up with an actual star. And so there's been done a lot of work about it, but we will start from 1998. This is the year when Testia Sargent found that the slope of the core mass function, which is the statistical mass distribution of prestellar cores, and in particular the slope at the highest mass, was in agreement within the same fragment of the initial mass function, so the statistical mass distribution of main sequence stars. So they interpreted this result as a hint that the main sequence stars were already set during the prestellar phase. There was a lot of discussion, and by passing the time, the Herschel-Gulbet survey project was ongoing, and it observed all the forming regions within 500 parsec in the Gulbet. And as you can see here, this table summarizes the fact that the slopes of different regions can be actually very different among each other, not being in agreement with the initial mass function. Sometimes there is not even a power law. So in a sense, we can say that the main sequence star is not already set during the prestellar phase. So if we really want to answer this question, we have to investigate later stages. We have to study the young stellar object. So in this talk, we will focus on the protostars that can be either class 0 or 1, and the premium sequence stars, also named class 2, also named classical Qatari stars. Zooming in on how a young stellar object is formed, how it behaves, there is a forming object. Of course, this is the simple scenario when we only have one object. There could be binary system, multiple system, but just go with the easy scenario. Then there is a gas disk, a dusty disk, and all of this is into an envelope. At least at the very beginning, there is this strong envelope. The envelope on class 0, so right after the core collapse, is so important that the ECD, the spectral energy distribution, peaks to, well, around 100 microns. By passing the time, the envelope dissipates, and we can start seeing something on the class 1 stage in the infrared part, near infrared part. But it's only when the star entered the class 2 phase, so the permanent sequence phase, that we can actually see the photospheric line of the forming object and being able to study those objects to short wavelengths. So let's start with the observationally easy things, classical Qatari stars. Everything that we know about accretion for the moment is actually based on the study of classical Qatari stars. And it is based on the so-called magnetospheric accretion scenario. So according to this scenario, the material from the outer part of the disk reaches the inner part of the disk. We still don't know exactly how, this happens. It's probably because of the viscosity of the disk, because of MHD winds, we still don't know it. But somehow it reaches the inlet part, and where it found the magnetic field line of the forming object, and by following them, it shocks into the forming star by accreting its mass. Of course, as long as some material is accreting the central object, some material has to be ejected in order to conserve the angular momentum. Here you can see an example. This is an X-shooter spectrum of a well-known class 2 arrow loop. And the UV excess and the near-infrared excess is what actually traces the accretion and tells you that this is a young star. But there are also other traces of accretion, all the lines that you see here listed in blue, mostly the hydrogen line, Balmer, Paschen, and bracket series. And there are also tracers of winds that you can see here in green, forbidden lines. The only way by which we can directly measure the accretion luminosity, which is the amount of emission due to the accretion process, is by modeling the UV excess and fitting it with a photospheric template and the SLAC model. So this is an example on how this can be done. And the output of this process is not only the measurement of the accretion luminosity, but also of all the stellar parameters, so the mass, the radius, and the luminosity, because of the spectral typing. So there is a very huge literature about classical T-tauri stars, but I will focus on this result. So in 2016, Manar et al. Found the existence of a relationship between the mass accretion rate and the dust mass of the disk. Now, this is for lupus, in the lupus star-forming region. The existence of such relationship was actually predicted by the viscous model. So at that time, we're all, okay, finally we understood what is the driven mechanism of the accretion process. It's the viscous model, so the viscosity of the disk. But then by collecting a lot of data, not only on lupus, but on a lot of star-forming region, we found actually a spread in this relationship, and also some other models which focus was on MHD winds came out, and the result is that for the moment the debate is still going on. So in this moment, both the MHD winds and the viscosity model can explain our data. So the question is still there. And the natural question that came in my mind was, okay, so for studying classical T-tauri stars, we are not able to distinguish because viscosity and MHD winds. But because an evolutionary difference, maybe if we go backward in time and study accretion on protostars, we will be able to solve this problem and understand the driven mechanism of accretion. The problem is that it's very complicated, because if you remember, I told you that for protostars in general, the central object is obscured because of the veiling, because of the excitation, because of the presence of the envelope. So what happens is that we don't have access to the UVB part of the spectrum of these objects, and so we cannot directly measure the accretion luminosity. Luckily, some empirical relationships were developed between the accretion luminosity directly measured through the SLAC model and the luminosity of the accretion in the near infrared. Here you can see an example of the bracket gamma line, which is the strongest, the brightest accretion tracer in the near infrared. So the idea was to start from this and find a way to determine the accretion luminosity and then also the mass accretion rate. Even if for the mass accretion rate it's more difficult, because you need also the stellar parameters, not only the accretion luminosity. However, this relationship were developed with lupus data, and it is good to ask ourselves whether those empirical relationships can be applied to whatever region, whatever objects, and also whatever evolutionary stage of of the star formation process. And for this reason, I'm working in the worldwide collaboration releases Odysseus and Penelope, also to answer this question. So this is a very important collaboration studying classical T-Tauri stars. And basically the idea is to observe contemporary with HST, the near UV part, and with VLT shooter, the rest of the classical T-Tauri spectrum. At the same time, there are also observations with high resolution taken by either Espresso or use, depending on the UDT that will be available. So thanks to this large sample that spread, well, quite good in age and also is complete in mass, I'm currently studying about 68 young stellar objects, classical T-Tauri stars, for which all the stellar parameters and rates are well known in extremely detail. And thanks to this, I'm going to show you this. Those are preliminary results. But still, if you compute the accretion luminosity by using the slab field model and the accretion luminosity by using the lines, so empirical relationship, you find a linear relationship, at least linear within the error. So we can say that it's fine if we apply this method in general. Is it fine if we apply this method also for class 1s? Well, I say that probably it depends. For my sample, those are very bright class 1s, brighter than 14.5 magnitude in K-band. So I'd say that those class 1s I'm studying can be described are like very extincted class 2 in a sense. So this is what I've done. Yeah, here you can see so we developed a self-consistent method based on basically the empirical relations that I described and some assumption on the luminosity of the objects that we discuss. I assumed an age based on Spitzer's timescales, so it should be correct. And of course, to get the stellar parameters, I used evolutionary tracks. And what we found is that the mass accretion rate of class 1s that you can see here in black and pink is higher than the mass accretion rate of class 2 as a function of the stellar mass. Now, this is good. This is good because it is what is predicted by the models, so we're happy about it. But at the same time, if you look at the numbers and integrate those numbers for the time scales of class 1s, which is 0.5 mega years, according to Spitzer, it is not so good because, I mean, it means that most of the stellar mass is not built in this stage. So we should investigate this far. However, in this work, we observed only 10 objects in a single cluster in Perseus. So of course, this can be not general. And the next step was to generalize it. So I collected a sample of 60 class 1, bright enough to be observed from ground-based facilities. And this is what I get. So looking at the accretion luminosity as a function of the stellar luminosity, you can see that there is a very nice evolutionary trend. And actually, the class 1s I analyzed lay in the same distribution of class 2. So it seems to work in a sense. Looking at the mass accretion rate, you can see that the result previously obtained for Perseus is actually confirmed in general for all those targets that were collected among different star-forming region within 500 parsec. So the problem is still there. The mass accretion rate is not high enough to explain most of the stellar mass. Now we have like two possibilities. First, it's not the class 1s, the stage when most of the stellar mass is accreted, and it's even before the class 0 stage, or it is not, the magnetospheric accretion scenario is not the most fundamental and maybe is not the only scenario, the only accretion theory that works to build the stellar mass. There could be others. For example, a possibility could be the so-called eRuptIve accretion. So to investigate this possibility, we studied the instability disk regime of our object. We also include in this plot our other class 0 and 1 from the literature. And you can see that most of the protostars that we study lay in the blue part, which is the instability disk regime region as described by Crater and Lodato. Now, the instability disk is what we think triggers the eruptive accretion. So, in a sense, this is suggesting us that eruptive accretion could be more important than we think in building the stellar mass of young stellar objects. However, the problem with this theory is that we only know about 60 eruptive young stars, and not only in the nearby galaxies, but in general. This is a problem because if we approach this problem as a statistical problem, there are not enough objects to explain the building, the fact that that eruptive accretion is the reason why we build our stellar mass. So what we were doing now is to looking for more objects, because it can actually be a problem of bias. The time scales of those objects can be short, can vary a lot from days to centuries, but can be short. So this can actually be an observational bias. And with Glorious international collaboration, we look at Gaia photometric science alert program. And when an object is elected, like, for example, this is the case, when you can see here the black dot, it means that according to Gaia, this is a candidate of eruptive young stellar object. We ask for spectroscopic follow-up to confirm or not the eruptive nature of these objects. And thanks to this, we discovered in the last years up to 12 new eruptive young stars. Now, it's not a lot, but since we were starting from 60, is however something. And the higher the number of the eruptive stars and the more robust the statistics to understand the role of eruptive bursts on the stellar mass building. So here it's really a matter of numbers. However, a possible the fact that the eruptive accretion could explain the built mass of young stellar objects was something debated a lot. Historically, the problem of not having enough eruptive objects was known as the protostellar luminosity problem. Now we are more we like to use another word. We talk about the protostellar luminosity spread. And in summary, according to models, there is a relationship between the luminosity of the young stellar objects and the mass accretion rate. And I mean, you can understand it because the mass accretion rates depend linearly by the accretion luminosity, so it makes sense. And according to the models, to explain the mass distribution that we have, during the class 0 and the class 1 stage, we should have 10 to the 1, 10 to the 2 solar masses, solar luminosity for most of the protostars. But those numbers are numbers that we actually see only for eruptive stars. But passing the time, we also discovered that the situation is even more difficult because young stellar objects are highly variable. And here you can see that there are really many different kind of variabilities, and which varies a lot in amplitude and also in time scales. So it's not an easy task, being able to explain the discrepancy that we see between the models and the observations about the luminosity. But what we have now is that there are a lot of models that can actually explain this. I'm not going into much detail, but now we do have another problem. We do have the problem that there are many different models that can explain this discrepancy, and we don't know which of them is true. Luminosities alone do not seem to provide enough diagnostic power to distinguish amongst these models. I'm using Fisher words. So again, what we have to do, we have to measure accretion rates and stellar parameters. This is extremely important. Okay, coming back to the other hypothesis, the main accretion stage is class 0. Okay, but class zeros are very difficult to observe. There is the envelope. There is no way we can see through the envelope the photosphere, or at least this is what we know. Recently, Leguilec et al. Analyzed a sample of class 0, you can see here in red, comparing it to the class 1 sample that you just see in the slides before. In particular, the comparison is between the bracket gamma luminosity, okay? So they haven't computed the accretion luminosity, not yet, but they are just comparing the luminosity of the bracket gamma. And according to the results, actually class 0 seems to, well, have higher luminosity bracket gamma lines. That's interesting, but the other interesting thing is that they found that actually some class 0 show some photospheric lines. And this can be due to the inclination of the object. There are hypotheses because of this. However, this is promising, and the next thing that we have to do is compute the mass accretion rate of those objects, of course. But there was also another task that will be extremely useful, and is to explain the empirical relationship that for the moment we have only up to near infrared to the mid infrared. Why? Because in the mid infrared, all the class 0 and 1 are brighter, so everything is easier, and hopefully we will be able to get new results. This is a very nice moment to do this because there is already JWC and Aries or Cryos at BLT, but also in the next future there will be METIS at TLT, which is basically perfect for this kind of scientific purpose. Okay, so really briefly, if you remember, we started from the fact that we wanted to compare the relationship between the mass accretion rate and the disk mass between class 2 and class 1. And now that we have all the parameters that we want, we can do it. So in this work, we presented for the first time the existence of such a relationship also for class 1. But if you look at the slope is different and not in agreement with what predicted by the viscous model. We investigated our sample with the isochrons, looking for the initial conditions. Basically, isochrons are locus in this diagram that can give you the initial disk mass to get those objects here. For example, in this case, our initial conditions spread from 10 to the minus 2 to 1 solar masses. And we also finally compared our observation with models. Looking at this plot, you can see that the viscous, not the wheel, and not the hybrid, meaning between viscous and winds, where both viscous and winds plays an important role, are able to explain the trend from class 1 to class 2. And mostly it's because of those objects. And by investigating those objects, we understood that those objects are strange in a sense because their depletion time, which is the time by which the disk is completely dissipated, is too short. It's just too short, shorter than 10 to the 4th years. So there are many possible interpretations for this, but what we've done is to ask for more data to understand whether those objects were only outliers or not. And another thing that is extremely important is to study in general this mass of protostars with SCA, because only going also adding centimeter data to our ALMA data, we will provide more accurate disk estimate. This is the last slide because to complicate all this picture, occurs a discovery made by Jaime Pineda et al. In 2020 that actually found some so-called streamers. So material coming from the envelope, not passing through the disk, but coming directly to the central objects. and we don't have an explanation for that. Moreover, we are finding those streamers also for more evolved objects, class 1 and class 2. So the situation is very complicated if we want to answer the question how the stellar mass is built, and we still don't have an answer. So I'm leaving you with the take-home messages that are basically that measuring the mass accretion rate is important. Is very important. We should focus our attention on protostars in general and also on eruptive objects because they are telling us more than what classical Centauri stars have told us to the moment. And however, we should also take into account the streamers when we found to, on one side, develop models to explain all of the observation, and on the other side, interpret our observation even when we talk about accretion. And thanks for your attention.
Thank you so much. It was really nice also showing all the various difficulties that we encounter. So, are there questions in the room?
Yes, it's like totally maybe it's a late question. So I think the last slide that you showed. So these streams of mass that comes not throughout the disk but from other direction, if I understand correctly. This could this help in explaining the build-up of the mass star. So I mean, you present this as a challenge, like something challenging for the models, but if I understand correctly, this would help the problem of explaining how we build up the mass of star.
Sure. The problem is that there is no way for the moment, by which we can constrain the mass accretion rate. I mean, here I reported some estimates, but those estimates, I mean, the error bars on those estimates are very large because they're based on basically assumptions because we don't know the stellar mass. And the stellar mass, I mean, basically you compute the mass accretion rate by knowing the accretion luminosity, the stellar mass, and the stellar radius. And the stellar parameters for class 0, I personally don't know how we can obtain them. So we don't know how much this is important for building the stellar mass
details
of the forming star. Yeah. Okay. And the problem is that now that models are time consuming, so either you start from the classical Centauri stars and go on more evolved disk, or you start from the core collapse and you go, well, even before at the beginning of the class 0, for sure you don't take into account the class 1s. So we cannot even compare something. I mean, we don't have parameters to observe to be compared with models. And under an observational point of view, for the moment, I personally don't believe those numbers because, I mean, we have to know that there are a lot of assumptions here. So this could be completely different. So yeah, it's important, but the problem is that we don't know how much it is.
Ooh. Yes, go. And then you are.
At some point you mentioned some instability in the disk. Can you tell more about which kind of instability it is and how it's related to this eruptive?
Sure. Okay, I think you're referring to this slide.
Yes.
Okay, so the instability is basically the gravitational instability of the disk. Also, in this case, there are different models. In this particular case, we focus our attention on this by Cratterente Lodato, which is promising. And basically, the fact is that a disk, in order to be there and rotate together with the star and around it, needs to have some stability between the kinematics and the mass. So it can be that the mass is so massive because of the material coming from the envelope that at a certain point it's too much and it has to get away from the disk. And in some cases, there are winds that just dissipate this mass. so you don't have any instability. Sometimes the disk just gets larger and larger, so you don't have the instability. But sometimes this instability occurs, and so you have those strong outbursts that partially accrete the central objects and partially just the material gets launched by outflows. So this is the instability. And we think that this is the reason why we do have eruptive accretion. I mean, we have observational constraints that highly suggest that this is the mechanism. But there are also other theories that complicate it. And so
Nice presentation. I think I'm confusing something. Eruptive accretion and eruptive young stars are basically the same, or?
Yeah.
And we see just few number of them because it happens in a really short time, or because the detection of them could be really hard?
I mean, the time scales are short. Well, I'm talking about eruptive accretion because they are different kind of eruptive accretion, and I'm not going into much details. But just as a reference, the eruptive young stars whose bursts last longer are fewer, and the order of magnitude of the time scales of those outbursts are centuries. So we are looking at objects whose lifetimes are mega years. So centuries are short with respect to mega years. So it could be, it could be possible that we are not observing so many of them, because even the most the most intense and the one which lasts longer are short. So that could be an explanation. For this reason, we're starting looking not only for the eruptive phenomenon, but also for some indicators in the disk that gives you a hint of the fact that some eruptive momentum happened in the past. And that could be done, for example, with gamma data, if you look at the Iceland. This is another way by which you can say something about the instability of the disk, which is also related to the eruptive accretion. But yeah, it could also be because of, an observational bias. Like with Gaia, we observe more objects, so maybe with the next generation of instruments, we will also be able to observe more objects.
Do we expect to have a different number density in different redshift for different types of galaxy because of these kind of extreme or these eruptive young stars?
Okay, so everything I told you about is within 500 passes. Only for the Gaia alerted eruptive stars, there are some at 1.5 kiloparsec. So we're not talking about redshift.
I mean, the expectations of the models or predictions that would be.
The only thing is that the far away you go, and the metallicity can be different. So there are recent papers claiming that the accretion rates are different, like for example in the Magellanic Cloud. But there is no spectroscopic follow-up, so it's tricky. I think that we could have the answer to this question, starting with cubes, that it's a next generation instrument at GST, and definitely with UST. But for the moment, we don't have the sensitivity to go far away, because the problem is that far away, there are a lot of stars. It's very crowded, and it's very challenging to see in detail a single forming star. So about models, I don't know. I don't even know if there are models. Maybe there are, but I'm not familiar with it. Sorry.
Oh, I'm really naive.
Question related to the beginning. Okay, at the beginning of the presentation, you have shown that the mass function of the cores is in some cases different from those of the initial mass function.
Yeah.
But I've noticed that in some cases, also unbound clouds cores are considered. So I was wondering if that can make a difference with the results.
Mm-hmm.
And if this also implies that you need a different efficiency of the accretion at a given, let's say, mass of the star that you want to produce, and if you see the difference.
Yeah, so that's true. The point is that the definition of prestellar core is quite uncertain. So we found differences between regions, also because of the distance, if you look at those numbers. Like, for example, the unbound core types are for the closest regions. Lupus, whose spread in distance is between 150 and 200, has no power law. And then for the farthest region, we still have this result. This is serpents, by the way, so it's the result is confirmed by Herschel. So so according to Annabelle, and I think I agree with it, with this, the point is that A is the resolution of your instrument. And the real definition of prestellar core, how can you tell, like, the ISM is spread, and you do have some densities, over densities, but the higher the resolution is, and the closest you are, and the higher the number of substructure that you can find. So how can you define a prestellar core? With Herschel, we see differences within 500 parsec, and with ALMA, we discovered that those prestellar cores can be extremely complicated. So yeah, I mean, if you're interested in this, I really recommend you this review by Patrick and Bell, where all this story of prestellar core, core mass function and sun mass function is summarized. And yeah, I can say that in the end, there is a debate whether the proper definition of prestellar core is valid, not depending on the distance, not depending on the resolution, and so. I answered your question.
Okay. Okay, so then let's thank Eleonora again.
Thank you.